This is section 3.1 on exponential functions. So an exponential function is a function where the variable, or the x, is in the exponent. So when you see here, f of x equals a to the x power. A has to be greater than 0, it cannot equal 1, and x is going to represent all real numbers. So for the graph of an exponential function, you're going to see that it's going to go up really fast or down really fast, depending on the type of function. And it's going to get close to some type of a horizontal asymptote, depending on the equation. For this one, it gets really, really close to the x-axis or to 0. Okay, so rules for transformations of a graph. We've talked about these rules before for other functions, and it's the same rules. It just looks a little different on an exponential function. So addition or subtraction with the x produces a horizontal shift in the opposite direction. So when you say a to the x plus or minus c, if it's a plus c in the exponent, then it's going to go to the left c spaces. Minus c would be to the right c spaces. So it does the opposite of what you would think when that number is in the exponent. Addition or subtraction outside the x, or not with the x, produces a vertical shift in the same direction. So a to the x power and then plus or minus c. If it's a plus c, it's going to go up c spaces. Minus c will be down c spaces. A negative with the x produces a reflection across the y-axis, so it's going to go left and right. A negative outside of the x, or in front of the variable there, in front of the base, is going to produce a reflection across the x-axis, so it's going to go up or down. Okay, the natural base e. So e is another special number in math, kind of like pi, that comes up a lot when you're dealing with financial type situations or exponential functions, and we're going to use it a lot in this chapter. So e is approximately 2.718281828, and it goes on infinitely. So it's just a special number. You can pretend it's a variable, or you can just understand that it's always going to be this number. There is an e button on your calculator, and so when you look at the function e to the x power, that's just some number raised to the x power. Now this graph looks a lot like the last graph, but the last one I actually used 1 to the x power when I typed it in the calculator. This is e to the x, which would be 2.71 raised to the x power. So they're going to look pretty similar. Okay, so the one-to-one property in an exponential equation says that if two bases are the same, then their exponents are equal. So if I have an equation like 9 equals 3 to the x plus 1 power, and I want to solve this, right now I don't have a way of getting that exponent down from, or the variable down from the exponent. So our goal is going to be to try to get the bases to be the same on the left and right side. So I know that 9 is 3 squared, so I'm going to change 9 to 3 squared and keep that equal to 3 to the x plus 1 power. Then using the one-to-one property, I can drop the bases because they're the same, and I'm just left with the exponents. 2 has to equal x plus 1. So when I solve that equation, then x equals 1. So your goal with the one-to-one property is to get the bases to be the same and then solve the equation for the exponents. Okay, so let's look at some examples. We're going to practice graphing first. So I've got the two functions y equals negative 2 to the x and y equals 5 minus 2 to the x. So these are very similar. The second equation is slightly different. It's got the 5 out in front. So if you type into your calculator the y equals negative 2 to the x power, we're going to make a table of values and then plot those points and see what it looks like. So y equals negative 2 to the x power. I'm going to go to my table, and I've just picked an assortment of points. You just kind of have to scroll up or down and find the best ones that work for you. So I'm going to plot these points. So I'm going to plot -1, -0.5, 0, -1, 1, -2, 2, -4, and 3, -8. So you can also hit graph on your calculator and then connect the dots and see what it looks like. Okay, same thing for the second equation. These equations are the same except for that 5 at the beginning of the equation. This would be the same as if I wrote the equation -2 to the x power plus 5. So to me, that plus 5 is going to indicate it's going to be the same graph as the first one, just shifted up 5 spaces. So you can still go to the calculator, type into the y equals 5 minus 2 to the x, and then we're going to go to our table and plot some points. So here's the points that I picked. And I'm going to plot those. So -1, 4.5, 0, 4, 1, 3, 2, 1, 3, -3. And if you compare those to the table on the left-hand side, you'll notice that the y values are all 5 more than the y values that we had before. So that graph has just been shifted up 5 spaces. So that's what that 5 is going to indicate to me. I always want to look at an equation and think about, okay, what are these numbers doing to the graph as I think about it? Okay, so on this one, I have 3 to the x minus 2 power plus 1. So when I'm thinking about this, I see the -2 with the x, and that's going to indicate to me something is going to be shifted left 2, or not left 2, right 2, because it's the opposite of what we would think. And then the plus 1 by itself is going to be up 1 space. So you think about an exponential function, it's going to kind of be shifted to the right 2 spaces and up 1 space. Okay, so we're going to type this into y equals and get some values from the table. Here's the ones I picked. I just rounded. And any of the ones that were decimals, I rounded those to the nearest tenth. I tried to find some whole numbers, and I just picked these. So -8, 1, 1.3, 2, 2, 3, 4, and 4, 10. Okay, so there's the graph of this exponential function. So you can see it's not sitting on the x-axis like our very first equation one. It's shifted to the right and up. Okay, this one's a little different. It's got an e in it. Works out the same way. You're going to type into your calculator 2 times, find the e button, e to the x minus 2 power plus 4. So this tells me, since it's -2 with the x, that's going to be right 2 spaces, and then the plus 4 on the end tells me up 4 spaces. Okay, so I go to my table and I pick some values. Because it's e is that weird decimal 2.7181828, we're all going to have lots of crazy decimal answers in our table here, that not everything is going to be a whole number. So you just round those to the nearest tenth and pick the best ones. Okay, so I'm going to plot these points and then connect the dots. Okay, now we're going to use the one-to-one property to solve these exponential functions. So I have 3 to the x plus 1 power equals 27. So my goal is to get the left and the right to have the same base. Well, 3 is the simplest base that I can have. It's a prime number. So I'm going to leave 3 to the x plus 1 on the left. But on the right, I can change 27. So I think about 3 to what power would equal 27? Well, if you're not sure, just try it on your calculator. Raise 3 to several powers just so you can figure out what it is. but it turns out 3 to the third power is 27. So once you have the bases are the same, you can drop the base and set the exponents equal to each other. So x plus 1 equals 3, and then when I solve, I'm going to get that x equals 2. Okay, well, you always want to check your answer to make sure that works. So we're going to plug 2 back into our equation and check our work. So if I do 3 to the 2 plus 1 power, I want to know, does that equal 27? So 3 to the third power, does that equal 27? I type 3 to the third in my calculator, and we already know it does equal 27. So x equals 2 is the correct answer. Sometimes when you plug it back in, you get a number that doesn't work, and you just wouldn't include that as your solution. You would just mark it out. Okay, number 5. This one's a little less obvious because we don't have any simple bases here. So I've got 64 to the 2x minus 2 power equals 1 over 16. So I want to try to figure out something that 64 and 16 have in common. And there's several different options you could choose. I'm going to go with a base of 2 because I like to think about prime numbers. So I have to figure out 2 to what power equals 64. So I know that 2 to the 6th power equals 64. So whatever that new exponent is will actually get multiplied times the old exponent that's already there. Now on the other side, I have to figure out, well, what is 1 over 16? So don't let the fraction freak you out. Just ignore the fraction and think about the number on the bottom. Well, I know that 16 is 2 to the 4th power. And anytime you have an exponent in a fraction, if you want to move it to the other side, you just make the exponent negative. So 1 over 2 to the 4th is the same as 2 to the negative 4 power. So 1 over 16 is the same as 2 to the negative 4. So I'm going to put equals 2 to the negative 4 on the right-hand side. So now that the bases are the same, I can drop the base and set the left and the right equal to each other. So on the left, I went ahead and distributed the 6, and I got 12x minus 12 is equal to negative 4. Now I'll just solve. So I'm going to add 12 to both sides, and I get 12x equals 8. I divide by 12, and when I reduce, I get that x equals 2/3. Okay, so I need to check my work. So I want to see 16 raised to the 2 times 2/3 minus 2, is that equal to 1 over 16? 64 raised to the 2 times 2/3 minus 2, is that equal to 1 over 16? So in my calculator, I can type 2 times 2/3 minus 2. And that gives me negative 2/3. So I've got 64 raised to the negative 2/3, and I want to know, does that equal 1 over 16? So if you type 16 to the negative 2/3 power into your calculator, you get 1 over 16 when you convert it back to a fraction. So that means that 2/3 is a solution. Okay, number 6. Same thing, using the one-to-one property. So I have 3 to the 2x power equals 3 to the 2x plus 2. The bases are the same, so I can drop the base and set 2x equal to 2x minus or plus 2. So when I try to move the 2x's to the same side, you notice that the 2x's cancel. But I've still got 0 equal to 2. Well, 0 doesn't equal 2. 0 doesn't equal anything other than 0. So anytime you get something crazy like that, that means there is no solution. There's no number that I could plug in where these two are going to equal each other. Okay, number 7, we're going to use the one-to-one property again. It's just this time we have base E. So notice on the left and right, both of these are base E. So since they're the same base, I can drop the base and set the exponents equal to each other. So anytime you have a trinomial, you have an x squared, an x, and a number, you have to move everything to one side of the equation. So I'm going to move the 2x over to the other side. So x squared minus 2x minus 3 equals 0. To solve a trinomial, you have to factor. So I need to know two things that multiply to get x squared. So that's x and x. And then I need two numbers that multiply to get 3, but add or subtract to get negative 2. Well, the only thing that multiplies to get 3 is 3 and 1. And to get the negative 2, it would have to be a negative 3 and a positive 1. So then I set those factors equal to 0 and solve. And it turns out that x equals 3 and x equals negative 1. So I need to plug both of these back in one at a time and find out if one or both of them are solutions, or possibly neither of them are solutions. So let's start with 3. So if I do e to the 3 squared minus 3, I want to know, is that equal to e raised to the 2 times 3 power? So on the left-hand side, 3 squared minus 3 is going to be 6. So e to the 6, is that equal to e to the 6th? Well, yes. Some number raised to the 6th power is the same as that same number raised to the 6th power. So that is true. That works. Okay, let's try negative 1. So e to the negative 1 squared minus 3, is that equal to e to the 2 times negative 1 power? So negative 1 squared minus 3 is going to be negative 2. And then on the other side, we also have e to the negative 2. So this one also works, which means that both of these are solutions.